Okay, this is scenario 3, and this is the confidence interval for a paired t-test. So this will be our third scenario and our final scenario for this section. So investigators at the U.S. Department of Agriculture wish to compare the methods of determining the level of E. coli bacteria contamination in beef. We have two different methods, A and B, of determining the level of contamination, and they were used to each of 10 randomly selected specimens. So we have 10 specimens, and each specimen received an A test and a B test. So we should have 20 readings in our table. The data obtained in millimicros per liter of ground beef for each of the following methods are shown in the table below. So we have piece of beef or liter of beef 1, etc., our different liters of beef, and we have 10 of them, and we have a reading for a type A and a type B. So in fact, we do have 2 readings for each liter of beef or each piece of beef. So consequently, we have a paired test because it was tested once. This liter was tested with method A, then method B, then method A, and so on and so forth. So each one was tested twice. So we can say that this is going to be a paired test. So create a confidence interval for the mean difference. Does your confidence interval indicate the detection methods are different? Justify your response. So let mu D equal the true population mean difference in the detection methods for E. coli, A minus B. So first off, we have to state that we're working with the mean difference. Next, we need to say which way we're going to subtract, and we're just going to go A minus B because A first, then B. And our conditions, we're going to go ahead and say they were assumed. All right. They gave us a random sample, etc. Here's the actual information. Because you may need to be doing this in your college course. It depends on the school. It's definitely required for the AP, but not for our class. Okay, so the next thing is I need my equation. And my equation for this is simply X bar D X bar D plus or minus T star SD divided by the square root of n. So first off, X bar D, we don't know that. SD, we don't know that. N, we do know that. We have 10 pairs. So basically, we have 10 groupings or 10 pairings. So even though we have 20 readings, we have our sample size is 10. We're going to need our T star, and we're going to need our degrees of freedom. Well, we don't know T star. We can go ahead and say our degrees of freedom are 9 because it's just 10 minus 1. All right. So how am I going to do this? Well, the best thing I can do is at this point, take my list of data and enter it into column L1 and L2. So stat edit. And if you have extra columns, arrow up to the one you need to clear out, clear, enter. So I've entered A data or method A into L1 and method B into L2. So I've entered all that data, so it looks something like this. But I'm not interested in the individual data. I'm interested in the individual differences. So I need to go to the top of L3 and go second one minus second 2. And now I have my individual differences. Okay? So I have all the individual differences, but I still don't have X bar D, etc. So we're going to go ahead and run the test. So stat test, and this is a T interval. So we're going to drop down to number 8. And the reason it's a T interval is because we're having to use the standard deviation of the sample. We're using the sample value. Make sure data is highlighted. Our list of differences in L3, so second 3. And we're supposed to be conducting a 90% confidence interval, so 0.90. And we get a bunch of information, some of which I need immediately, some of which I'll use in a little bit. First off, we do get our actual interval, negative 0.075. And then we also get a upper bound of 0.6550. XD is 0.29. SD is 0.6297. So the only thing I don't know right now is my T star. So we need to go back and calculate T star. So the second vars, inverse T, parenthesis, 1 minus 0.90, close parenthesis, divided by 2. Degrees of freedom are 10 minus 1, or just 9. And we end up getting a T star of 1.8331. And it's just easier to work with the positive values. So I can go ahead and plug those values in, and I get 0.29 plus or minus 1.8331, 0.6297 divided by the square root of 9. Square root of 10, I'm sorry. Please be careful. Square root of 10. Don't use your degrees of freedom, use your n. So square root of 10. All right. So then we write our interval down. This is my lower bound. Here's my upper bound. We need to record both of those. So we are 90% confident that the true population mean difference in detection methods for E. coli A minus B, we always have to give our order, which in this case is A minus B, lies within the interval. So that's the interval it lies in. In repeated sampling, we expect that this method will capture the true population mean difference in detection methods for E. coli 90% of the time. Now, when I look at this interval, it goes from negative to positive, which means 0 lies within an interval. And because 0 lies in the interval, that means we're unable to detect which method is better at detecting E. coli. All right, because 0 lies within an interval, we're unable to detect which method is better at detecting E. coli. All right, that'll conclude these. Thank you.